Hello, class. Just checking my microphone here. Yep. Okay. Yeah, that's good. Okay. This is our lecture on Poisson's ratio. We're sort of moving out of uniaxial stress, and what we're going to look at today is we're going to look at biaxial stress. And I'll look, boy, this isn't the pen to use, is it? I'll also look at triaxial stress. Just to introduce that, we're not going to, we'll look at a problem with triaxial strain, but it's not going to have triaxial stress. It'll only have biaxial stress, but I'll go through the equation as to what would happen with triaxial stress too. All right. Really, though, this lecture is introducing Poisson's ratio and the non-conservation of, let's see if I've got a better pen here. Yeah, maybe that one's better. The non-concentration, conservation of volume. That's right, there's no conservation of volume. But we'll see that, you know, later on. So what I wanted to do first was introduce Poisson's ratio. And Poisson's ratio, let's say that I had, let's say I just had a uniaxial stress. And I'm going to try and draw this in 3 dimensions. And I'm going to exaggerate it a little bit too. Let's say that I had some type of, you know, long tensile bar like this. And I placed a strain on it, or you know, some type of force. So I'm pulling on it at this end with a force P, and I'm also pulling on it at this end with a force P. Now, what's going to happen to that volume? I think everybody can see. I'm going to use a different colored pen for that. In fact, I'm going to go to red. I think everybody can see that what's going to happen is this is going to get longer, right? It's going to get longer. I'm going to draw it as if we could actually see, you know, through the steel bar that is there as it is now. So I'm going to draw the entire bar. Right, so you can see it. So this would be, I'll draw the visible end of what it would look like here, right? Because it would be longer, and then it would also be longer back here too, but it would be narrower. Does everybody see that? It's narrower in the 2 directions, but it's longer in the 1 direction. So if we were to say that this is the X direction, and this is the Y direction, then this would be the Z direction. Does everybody see that? It's a right hand thing, so if I were to lay my right hand and curl my fingers, X toward Y gives me Z. That's why it's an XYZ right-handed coordinate system. Almost all the coordinate systems that you're going to ever work with at undergraduate level anyway, whether it's Cartesian coordinate systems, cylindrical coordinate systems, or spherical coordinate systems, they're all right-hand coordinate systems, right? All right-hand. Cartesian, cylindrical, they're all right-handed. And what I mean by that is that if you lay your right hand along the x-axis, that's why it's XYZ, not YXZ. And it works that way in the alphabet too, doesn't it? And curl your fingers. Your thumb will be pointing in the positive Z direction. So X, y, z. X crossed with y gives me z. And of course, that's what it would be, right? Okay. Anyway, I probably even mentioned that before in an earlier statics thing. So what we've got here is we're going to have strain in the x direction in this uniaxial problem, aren't we? So what is the strain going to be? Well, let's remember Hooke's law. Hooke's law in the elastic region says that stress is going to be proportional to strain, right? Let's not forget our stress strain diagram that we're looking at. We are only looking at, remember, this first part right here, right? The elastic region. We're only looking at the elastic region. And in the elastic region, it's all linear. And so, and we really look at, you know, getting out of this where we've got permanent deformation outside of the elastic region. Like if I were to go into the plastic region out here, let's say that I went past the, I'll use green. Let's say that I actually went up, right? I'm loading and loading and loading this thing. And if I unloaded it, it would come right back down. So if I loaded it all in the elastic region, I can load it and I can unload it. I can load it and unload it. Load it and unload it. Doesn't matter. It's always going to come back. It's like me pulling on this plastic here, right? Oh, it's longer. Now it's the same length. Now it's longer. Now it's the original length. Now it's longer. Now it's the original, right? Because it's going, it's elastic. That's what we mean. It's like a rubber band. It goes back and forth. But what happens if we go into the plastic region? If we go into the plastic region and start to stress it there, when it comes back along the first elastic region, right? So then there is a permanent deformation. Permanent deformation. You can see, so as we go into the plastic, and that's how things stretch. So, you know, if you bend something, if I bend a piece of metal, you know, I'm bending it into the plastic. If that bend remains in that piece of metal, then I've stretched it into the plastic region. The elastic region, everything comes right back. So that's what I'm saying. If I'm staying in the elastic region here, and of course I've exaggerated how much this is going to decrease in cross-sectional area, right? This is going to be the new cross-sectional area, right? Right there. I'll cross-hatch it both ways so everybody can see that, and then I'll outline it. That's the new cross-sectional area, and the old cross-sectional area, of course, is the big black box that we had there. So it stretches out, but it gets thinner. So it's getting thinner in both of those two directions, but it's getting longer in this direction. So that's what I wanted to look at. What is the strain in the x direction? Well, let's just look at this, right? So the strain in the x direction is going to be the stress in the x direction divided by the modulus of elasticity. And when we think of the modulus of elasticity for steel, right? The modulus of elasticity for steel is about 200 gigapascals. And of course, that's the slope. That's this slope right here, right? This is E. It's a straight line. Y equals mx, sigma equals E times, which is the slope, times strain. I wrote over that, so I'll write it again. Okay, so that's what we've got. We've got the strain in the x direction. Then what we know, because it's getting smaller in the y direction and the z direction, it's getting smaller, isn't it? So the strain has got to be negative in those two directions. So the strain in the y direction is Poisson's ratio. That should be going up like that. Poisson's ratio, I'll talk about that in just a second, times the strain in the x direction. Okay? Now, and of course, that's a negative because excuse me, I just had a sip of tea, went down the wrong path. So I'm pulling in the X direction, so that's going to be a positive, right? But this is going to be a negative because it's going in, it's getting smaller. And of course, that would be the strain in the Z direction too, would be negative times Poisson's ratio times the strain in the X direction, okay? Now, I want to do an example problem. I'm going to say that this original length right here is 1 meter, right? So my original length, this is, just put these up here as equations that we're going to be using. And I'll just write some things here. So my original length is 1 meter. My original cross section, which would be this area up here, I don't want to do that in black. I don't even want to do it in green. I'm going to do it in orange. So my original cross section, that was this larger rectangle, or actually square up there, was going to be, is going to be 4 square centimeters. Okay, so we've got 4 square centimeters. That would be 2 centimeters, 2 centimeters by 2 centimeters if you wanted to make this square. So 4 square centimeters is my cross-sectional area. I gave you the modulus of, yep, that's what we're going to use in this for steel, because this is a steel bar, 1 meter long steel bar that we start pulling on. And we're going to put a stress, right? We look at the stressometer and we see that we've got a stress in that bar of 40 megapascals. Now that's nowhere near the limit of a steel bar, right? Because usually, you know, really, when we look at the maximum, depending upon the type of steel alloy that we're talking about, we can have maximum stresses, you know, with some excellent steel alloys that are like 400 megapascals, 10 times the loading that we're putting on that bar right now. But this is what I want to put on the bar right now, just 40 megapascals. We've loaded the bar up. You're probably saying to yourself, hey, you know, if we know the cross-sectional area here, we can immediately figure out what the force P is, right? Well, of course we can. P, because we know that P is P over A is just a sigma. So P equals sigma times A. So 40 megapascals times, what is 4 square centimeters? We certainly can't put 4 square centimeters in there, can we? If I had to write 4 square centimeters, let's just put a little line down here. If I had to write 4 square centimeters in square meters, what would that be? Would I divide it by 100? Would it be 0.04 square centimeters? That would kill everybody on that plane you're designing, wouldn't it? That's right, it would kill everybody. Isn't it 100 times 100? 100 times 100, it's squared. It's squared, so it would be, I'm going to write it like this, even though I'm not a scientist, 4 times 10 to the minus 4 square meters, wouldn't it? Everybody remember that, especially when you're working with cubic meters, right? It's not, of course. I'm going to test you on that realization anyway. All right, now let's get back to this. So we divided that by 10,000. So that's why it's 4 times 10 to the minus 4. I would really write this as 400 times 10 to the minus 6, right? Because it would be minus 6 would be the next one. But anyway, it doesn't matter. We can write it in there. 4 times 10 to the minus 4 square meters probably fits in a little bit better anyway. So that tells us that P is 16,000 newtons, right? I hope I did that right. I've got it written down here, so I'm pretty sure that I did that right. Okay, so we know what P is now. That was one thing that we wanted to figure out. We also wanted to figure out what the strain in the X direction was. So the strain in the X direction. Again, we can go right back up here. The strain in the X direction is just the stress divided by E. So I've got 40 megapascals divided by 200 gigapascals. And that tells us that the extension in the X direction is I'll write it two ways, 0.0002 or 2 times 10 to the minus 6, right? Either way, it comes out the same. Do I have any units on that? No, because it's pascals divided by pascals, of course, and it's meters divided by meters. This is a dimensionless number. It's just a ratio. Think of it that way. Equals a ratio. And what does it equal a ratio of? It equals a ratio of the deformation to the original length. Doesn't it? So, what is our new length? Our new length after we pulled it, you know, the length from here all the way down to here. What's that length going to be? Not much longer. I've certainly exaggerated this, haven't I? Not much longer. So it's going to be 1 meter plus, and then when I just multiply this by a meter, by 0.2 millimeters. So it's going to extend 0.2 millimeters after I've put my 16,000 newtons on that. Now, 16,000 newtons, what does that equal? See how I get your mind working all the time like an engineer? That's what I want to do. That's what my job is. Because you're thinking, oh, 16,000 newtons, oh, God, that many newtons? How many pounds is that? Well, we divide it by 4.45, don't we? So that we can see that it's 3,595 pounds. Now that's a lot too, isn't it? So we can, you know, work in all the things. I'm just going to cross that out. I don't have to tell you that it's, you know, 3,600 pounds. It's a lot of force, and it doesn't extend it very far at all, does it? Now, hey, let's see how much the strain is in the Y and the Z direction. So we know that the strain in the Y direction is going to be the same as the strain in the Z direction, and it's going to be minus Poisson's ratio. Now we're talking about steel, so Poisson's ratio is 0.3, and it is for most of the crystalline metals. And if you were stuck on a desert island and you had to know Poisson's ratio, and you had to use something, go with 0.3, unless it's wood. I'm kidding, but. And yeah, on a desert island, what else are you going to have? Wood. Anyway, let's go back to this. So this would be minus Poisson's ratio times the strain in the X direction, which of course is just the stress divided by E. Or we could just use the strain too, right? So in doing this, that would be minus 0.3. Put the parentheses around there and the minus out in front, because the minus really isn't in the 0.3, it's really out in front. And then I should somehow erase that equal sign that I chopped off there. There you go, that's equals. Thank God for my eraser. And then times the strain in that direction, which is 0.0002, right? So that gives us, say, 0.000. I could just keep writing all of the zeros, but if I got that right, 2.2. Yeah. So, but let's, do we write it? Yeah, 2 times 200. That should be 200 times 10 to the, well, I'm going to have to I'm going to cross that out. That would be 200 times 10 to the 6. I don't even know what I'm talking about. Let's put it over here. E sub x in big bold letters is 200 times 10 to the minus 6. And so if I'm multiplying this, 0.3 times 0.0002, that gives me 60 times 10 to the minus 6. And again, no units because it's stress or strain. Strain has no units, stress is in pascals. So that's what I've got, but can I turn that now that I've got that strain, and I know that the strain, minus, now I know that the strain is the deformation over the original length. I know that this, right, was 2 centimeters. And so was this side here because it's a square, right? So this is also 2 centimeters. Right? So if those were 2 centimeters apiece and they're shrinking in, and I want to find out what the deformation is, the deformation is going to be a minus. I'll make that minus a little bit longer there, and I'm just going to multiply it by the 2 centimeters. And that tells me, well, should I just a second, let's do this. 0.02 times 60 exponent minus 6. And that gives me a deformation of minus 1.2 times 10 to the minus 6 meters, right? So if we're talking in millimeters, it'd be 1.2 times 10 to the minus 3 millimeters, or really what I could say is that this equals minus 1.2 microns. I think I've got that right. 60 times 10 to the minus 6, and then that was 2 centimeters. Yep, yep, I think that's right. So you can see that these are not going to change very much either when I put 40 megapascals on this. It's a bar of steel. We have an intuitive understanding for what a bar of steel, how much a bar of steel changes as we load it up. But you can see that's with 16,000 newtons on it. Of course, this is 2 centimeters. That's about an inch by an inch cross section for a steel bar. That's a pretty strong steel bar. So 16,000 newtons, or why don't I even put that there, approximately 3,595 pounds, so that we have a good idea of what it is being placed on that, right? A 1-inch square steel bar can handle that easily. So, and you can see that we really haven't changed much here, but this isn't really the problem that I wanted to I mean, this is just an introduction to how we would use Poisson's ratio to solve a uniaxial problem and look at how it shrinks in. Now, I want to look at this. We have a uniaxial loading, but we have strain in all 3 directions, don't we? It happens that the strain in the y direction and the strain in the z direction happen to be the same, and they always will be because we're only pulling in one direction. But, we have strain in all 3, changes in all 3 directions. So what I want to look at in this next problem, and I don't know if I can finish the whole thing, but I want to set it up anyway. So the reason, I'm going to tell you the reason that I'm doing it. It's sort of like we've been doing with a lot of things when we've been looking at area moments of inertia, centroids, centers of gravity. Remember, we were looking at mass moments of inertia and things like that for flywheels, for the dynamic side of it. And this is what we're doing here too, is what I'm looking at, what I'm going to look at right now is a biaxial stress state. In fact, what I may do is I may hold the problem till the next lecture, but I'm going to introduce what I'm talking about in a biaxial stress state. And I'm going to try to draw this in 3 dimensions. This is like a cross section of, let's say, a steel plate or something. And we know that the steel plate has forces that are pulling on it in 2 directions. Do you see why I say biaxial stress state? So this is a biaxial stress state, but biaxial stress. So it's pulling in the X direction and it's pulling in the Y direction, right? Now, also you can see that we have thickness because it's a sheet of steel, right? Let's say it's for a tank or something like that. I'll say that this is like 1 centimeter thick. In fact, if I was looking at this, this would be, if this was about 1 centimeter thick, in fact, not even 1 centimeter, about 6/10 of 1 centimeter, that would be the steel that is used in a scuba tank, right? Steel that's used in a scuba tank. Let's not really worry about the, how big this is, but I'll give it some dimensions. I'll say that this side here, we're just cutting a piece out of a large pressurized tank. And this is 10 centimeters, right? From here to here, and 10 centimeters from here to here, and 1 centimeter thick. So we'll say that the thickness is 1 centimeter, right? Now, here's what I'm going to say about this. And later on, I'm going to derive this for pressure vessels, because understanding biaxial stress, and there are other applications for biaxial stress, but probably the most common use for biaxial stress is when I have something like sheet metal that is being applied to a tank, some type of tank that is holding liquid under pressure. Maybe the pressure is only gravitational, mass being inside the tank, but or maybe we have a pressurized tank, and of course we've got those all over the place. I mean, nitrogen. We even had them at Wentworth until they got rid of that pressurized tank storage thing right next to the president's office. So I've got this, and what I want to say about that is that we've got 2 different things. We've got stress in the Y direction, and we've got stress in the X direction. Now, when I look at this for a pressurized, and like I say, I'll derive this in an upcoming lecture. But when I look at this for a pressurized vessel, this is called the hoop stress, right? And this is called the longitudinal stress, okay? Now, that's all I'm going to say about that until I get, well, I shouldn't say that, because in a pressure vessel, I'll write it right down here. In a pressure vessel, the hoop stress always equals twice the longitudinal stress. The hoop stress always equals twice the longitudinal stress. And that's why, I'll explain this. Well, actually, I'll explain that later when I derive it. But let's look at how this applies to this now. So now, all of a sudden, we've got stress in 2 directions. So if I wanted to look at so this is making this longer, right? It's making this longer, but it's making this thinner and this thinner. So let me just draw that over or as sort of an overlay on here. So this right here wants to make this longer, right? It wants to make this longer, just like I drew up there. That's going to be longer, but the other two ways are going to be thinner, right? In fact, I'm going to draw it down here too. So this stress in the y direction, but hey, wait a second. What about the stress in the x direction? Isn't the stress in the x direction wanting to make it longer in that direction and it thinner in this direction? Isn't that what the x direction wants to do? It wants to make it longer in this direction, right? And it wants to make it thinner in the other direction. Does everybody see that? Aren't those competing interests? Isn't this one, when I look at sigma sub x, isn't the strain in that direction sigma sub x divided by E? And the strain in this direction would be sigma sub y divided by E. But then, hey, they're also pulling each other in. So this is pulling it longer. Sigma sub y is pulling it longer. But then sigma sub x is pulling sigma sub y in a little bit too, isn't it? That's right. That is exactly right. If I look at the strain in the x direction, the strain in the x direction is the strain in the x direction, which would be sigma sub x divided by modulus of elasticity, right? But the stress in the y direction is pushing in the thing. So we have to subtract that off. So minus Poisson's ratio times the stress in the y direction over E. Does everybody see that? I thought so. Now let's do the strain in the y direction. The strain in the y direction is going to be the stress in the y direction over E. That's what's actually pulling it, making it longer. And then it's going to have subtracted off the stress of the Poisson's ratio times the stress in the x direction divided by E. Right? How about the strain in the z direction? Let's not forget about that. There's strain in all three directions, isn't there? There may be stress in only one direction or two directions, but there's strain in all three directions. So this is going to be minus, isn't it? Because in the z direction, this one is trying to squeeze it in, and this one is trying to squeeze it in. So it's going to be minus sigma sub y over E. Well, I can't write it there. Let's write it down here. Sigma sub z, or epsilon sub z, strain in the z direction, is going to be minus sigma. Well, I can write yeah, sigma sub x over E times Poisson's ratio minus sigma sub y over E times Poisson's ratio. All right? Because they're both minuses. They're both making it smaller. So let's simplify these a little bit. So if I were to look then at strain in the x direction, that would be 1 over E times sigma sub x minus Poisson's ratio sigma sub y. Let's put a blue line around that. Can you even see that's blue? That's not even hardly blue. I better get a red or a orange or whatever. Oh, and there the blue. The blue was so upset about that it jumped right out of the holder. You're kidding me. Well, it looks like we're really up to just about the end of it. What I wanted to do, though, is I wanted to simplify this out for the next two as well. So sigma sub x 1 over e, sigma sub x minus mu sigma sub y, and I'll just put a line there. And then sigma sub y, when we look at it, we can do the same thing, pull 1 over e out of there, and then we've got sigma sub y minus Poisson's ratio times sigma sub x. Somehow I'll put a thing around that. And then for z, we've got the 2. And in fact, what we can do is we can take Poisson's ratio out of the equation, and we could say it's minus Poisson's ratio over e, right, times sigma sub x plus sigma sub y, right? And that's why, don't forget it's a minus, because it's both of the two biaxial stresses are tending to squeeze and make the thing thinner. And getting there, what we're going to do with the next one is I'm actually going to roll this in there and look at a pressure vessel even before we get to more pressure vessel later on equations. And remember, for a pressure vessel, sigma sub h equals 2 times sigma sub L. What does that really mean? That means that if I have a scuba tank, say I've got a scuba tank like this, right? There's the end of it. And it's not a very good drawer, as you can tell. The scuba tank, this is the hoop stress. This is the thing that's tending to pull that thing apart, right? Because I'm filling it up with air. It wants to break right around here. So this is my hoop stress. Now I've also got a longitudinal stress, which is pulling in this direction, right? It never, any pressure vessel never breaks this way. It never blows up and separates that way. It always rips with the seam down the side. Every pressure vessel has that built in, that it'll rip with a seam down the side rather than blowing up. Got a great story to tell you about that when we get there too. All right, that's it for this lecture, and see you at the next lecture.